Okay. In this episode, we will talk about the Upwind scheme of CFD. So, what is the Upwind scheme? The Upwind scheme is an approximation used to give us a stable solution for convection problems. Okay, so we'll talk more about what stability is at the end of the video. And yeah, this is for convection problems. Convection problems. So I explicitly mentioned convection problems, meaning to say that we have to know each term. What is it? Is it a diffusion term? Is it a conduction term? Is it a source term? Is it a temporal term? Okay, so you have to know what is the convection term. And I've mentioned this in the second video on transport theorem. In that video, I mentioned convection terms are denoted by a first derivative with respect to phi. Okay, first derivative with respect to phi. And also, another way to know that if you're dealing with a convection problem is that a velocity of the fluid is explicitly mentioned. So the fluid has some velocity u. Okay, we usually denote the velocity u. Okay, so the fluid is flowing with some velocity, and the direction of the velocity matters. So if the value of u is positive, then in a one-dimensional problem, it's flowing to the right. If the value of u is negative, then the fluid is moving to the left. Yeah, some conventions that we use. Okay. So what is convection? Convection is a convection involves the transportation of a property, like for example temperature, or I think you might be familiar with convection in, like for example heat, right? Convection as a heat transfer process. So I think a lot of you are familiar that hot air rises and cold air sinks down. Or you can even have convection through forced convection, which you might be familiar in heat transfer. Forced convection is when we use a fan to blow some wind. Like for example, using a fan or an air conditioner to blow some wind and transfer heat, for example. But you can also transfer things like concentration. Let's say you have some gas, you want to transfer it over. It's also a forced convection problem. Yeah. So at the end of the day, convection involves the bulk fluid motion, the bulk fluid motion. So that's why it will always mention some velocity u. Okay, so let's dive right into the problem. A property phi is transported by the means of convection and diffusion through a one-dimensional domain sketched in this figure. Okay, so they explicitly mentioned u and the direction, so it flows to the right. There are some boundary conditions, and the length of this domain is L. So the governing equation is this. Boundary conditions are this. Using 5 equally spaced cells for the finite volume method together with the upwind differencing scheme, calculate the distribution of phi. So in the tutorials, I forgot to mention this in the previous videos, but in the tutorials, calculating the distribution of phi is they want you to calculate phi 1, the actual number of phi 1, phi 2, all the way to phi 5. But in the exams, as far as you are concerned, you do not need to get all these 5 values, because calculating this is quite a tedious task. We would usually involve a computer to do it for us. But in the absence of a computer, we can't do this, right? So as far as the exams are concerned, usually what we want you to do is obtain the equations. That's why in the previous videos, I stopped at the equations. I didn't bother to solve for the numerical values. Okay? Okay. So I'm not gonna do this. I'm only gonna do this 0.1 case, because 2.5 is just a matter of just changing the values that you substitute later on. Okay, so we have to use the upwind differencing scheme. So this is the values that you're going to use later. Okay, so now let's take a look at the governing equation. The governing equation shows us this. So let's take a look at this term and identify what is this term. This term is a first derivative with respect to phi, right? First derivative with respect to phi. So this is a convection term. Convection term. And you see the convection term contains u. It contains the velocity u. So we know it's the convection term. So this is the convection term. And what about this side? This side involves a second derivative with respect to phi. See, first derivative, second derivative. So this is a conduction term. Conduction term. So yes, so the question was right. Transported by means of convection and diffusion. Okay, diffusion is the same as conduction. Sorry, I should say conduction is a type of diffusion. Okay, conduction is a type of diffusion. So it's the same thing. The boundary conditions are this. Okay, so let's get right into it. So we need to calculate the distribution, meaning to say we need to get the 5 equations that will help us get all the values of phi. Yeah. So as always, we simply start out with the governing equation first. So you copy the governing equation. So let's copy the governing equation. So d dx rho u phi is equals to d dx gamma d phi dx. Okay, so what is our approach in dealing with upwind scheme problems? First, they tell us to use the finite volume method, right? Let's have a look. Tell us to use the finite volume method. So this is what we learned in the last tutorial. So always in the finite volume method, you first copy the governing equation, and after you copy the governing equation, you integrate both sides of the equation over the control volume. Okay, integrate it over the control volume means integrate with respect to x, integrate with respect to x, then the control volume, this is the control volume. So each of this are control volumes. Okay, so the control volume, take a look. Let's look at this control volume. The control volume is integrating from what? Take a look. Okay, we're integrating from is w to e. Okay, so we have to put our bounds of integral is w to e. W and e. Okay, so let's take a look how to evaluate this. So you see, integration is opposite to differentiation. Okay, so they will cancel out. The effects will cancel out. Okay, the integrals are an opposite effect to derivatives. So if I see an integration and I see a differentiation, poof, they will cancel. Okay, so this cancels with this, and same as this side, this cancels with this. So what we're left is the inside term only. So just copy that down. Okay, and you see now I have to evaluate this at these two bounds and subtract them. Okay, take their difference. So we have this term at east minus the same term, but then evaluated at west. Okay, copy this down. This term at east, this term at west. Okay, and all of these are constants. Okay, all of these are constants. All of these are constants. And same with this, gamma and gamma is constant. Well, actually, we can take them out. Okay, can take them out like this, like this. And I'm gonna factorize out gamma. Factorize out gamma. We have d phi dx evaluated at e minus d phi dx evaluated at w. So now we have to do our approximation, right? When we're stuck at all these e and w terms, we have to start doing our approximations. So in the last class, we are familiar with how to do the right-hand side, right? The right-hand side is just using the central differencing scheme. Whenever you're dealing with the diffusion term, you simply use the central differencing scheme, which is the immediate right minus the immediate left divided by the segment to deal with it. Now, remember, pay attention. Remember earlier I said that we have to be able to be clear who are the terms, the diffusion term, the conduction term, the convection terms, etc., etc. We had to be clear. Why? Because depending on where the terms come from, that is how we're going to do our approximation. So let us start from the very start. Yeah, let us go back to the very start. This is the convection term, right? Remember that this is the convection term. convection. And this side is the conduction term, or otherwise known as the diffusion term. So let me just call it the conduction term. Okay? And remember, where did we obtain this from? We obtained this from the convection term. And also, of course, this follows from the convection term. Okay? So this side comes from the convection term. This side comes from the conduction term. So the conduction term is pretty much what we learned in the last few videos already. So that part is not surprising. That part is familiar to you at this point, by this point already. The thing that is new here is how to deal with these terms, the convection terms. And this is where upwind differencing scheme, not upwind differencing, upwind scheme. This is where upwind scheme approximation comes into play. Okay, so let's have a look. The question is, what is the value of phi E and phi west? We don't know. We don't know. So let's have a look. So let's draw the general template, right? Now we are interested at what? Okay, because we're gonna reuse this a lot, let's call this equation star. Okay. So let me take a look at my solution. So now, first let's do this equation at the internal nodes, which is nodes 2, 3, and 4. So add 2, 3, 4. So we have let's just draw the general template. So first we have this east, west. Okay. So our question is, what is this phi E value and phi W value, knowing that we have a fluid velocity flowing this way, in this direction. Okay? Given this information, how are we supposed to find phi E and phi W? So let me tell you the answer right away, and I'll explain why is it the case. Okay? So by upwind scheme, phi E will be equal to phi P, and phi W is equal to phi big W. Okay? So why is this the case? Notice that, okay, let's focus on this first. Phi E is equal to phi P. Where is phi E and where's phi P? Phi P is here, just right beside phi E, right? Okay, let me rub away my notations. Okay. So phi E is here, and phi P is just right beside it. Okay. How did I get this conclusion from the upwind scheme? Actually, what you can think of is this velocity, this fluid velocity, actually pushes this value here is phi p. Okay, at x equals to p, the value of phi is phi p. What this u does is it pushes this value of phi p over into the immediate right. Okay, because the direction of u is towards the right, so the value of phi p is being pushed to the right. So that's why we can approximate phi e is equal to phi p. And the same thing. So let's have a look at the other pair of values. Let's have a look. Let's focus on this now. Okay. So where's phi small w? We don't know what phi small w is, right? So by the upwind differencing scheme, we can say that because we have a fluid flowing to this direction, to the right, the value of phi big W is being pushed towards the to the right because of this fluid velocity direction. So we can say that phi small w is approximately equals to phi W. So basically, I think you see what's the physical meaning of this now. We have some fluid is flowing in a certain direction, and because of this flow, we don't know what's phi E, right? Our problem is we don't know what's phi E, we don't know what's phi small w. So because of this fluid flow, it pushes the next value onto the unknown points, the phi E and phi W. So let me recap again. This flowing fluid, this flowing velocity will push the value of phi P onto phi E. And then this value of phi big W will be pushed onto phi small w because of this flowing fluid, okay? Just think about like wind blowing certain toxic gas into the right hand side, okay? Actually, I'm gonna raise Professor Ang Wai Tiong's analogy, and this is how I managed to understand the upwind differentiation scheme from his analogy. Okay, suppose this is the x coordinate, and then you're standing here. You are standing in the middle, so let's just call this U. And then we have a person here, person A, person B. Okay, we have a person here, and this is you. Okay, and let's suppose that there's some wind because of like I don't know a fan blowing. Then let's imagine there's a fan here, and then because of this fan, it's blowing some wind to this direction. Okay, so let's imagine that both these persons they take a fart. Yes, a fart. Okay, so person A farts. So we have fart A, and then person B takes a fart. Both of them take a fart at the same time. So fart B. So because of this flowing wind, these farts are gonna get blown to the side. So whose fart are you likely to smell? Are you gonna smell person A's fart or are you gonna smell person B's fart? Because the wind is blowing this direction, it's gonna blow away. It's gonna try to blow away fart B and blow fart A towards you. So let's say phi represents the concentration of farts, right? So it's more likely that you can say the fart concentration that you're gonna smell is actually from fart A. Yes. Okay. This is actually the physical interpretation of the upwind scheme. I'm not kidding. I'm not actually joking. This is how upwind differentiation scheme works. Like you have wind blowing in one direction. Someone takes a fart beside you. Two-person takes a fart beside you. Who are you likely to smell? I mean, whose fart are you likely to smell? It's the person like standing in front of you where the wind is like gonna blow the fart towards you. Okay, so this is how you actually get a physical interpretation of the upwind scheme. Okay, and this is why I said the fluid velocity actually matters. Okay, and I think you see why is the case now. It's quite obvious, right? So let's go ahead. Let's continue with our stuff. Okay, so knowing this, so let me go back. So what you would do is yeah. So let me start again. So at 2, 3, 4. Normally in the exams, what you would do is you write at 2, 3, 4. You give them the differential equation, and you can use this diagram. Okay. Okay. So I'm gonna recap again. We already have the differential equation simplified for us. So now we don't know what's phi E, we don't know what's phi W. So you check the fluid velocity. Fluid velocity is flowing this way, right? So this means we don't know what's phi E. So check. The wind is gonna blow the neighboring phi value towards E. So it's gonna blow this guy towards E. So we know by the upwind scheme, phi E is equals to phi P. Okay? And also phi W will be phi big W because we don't know what's this guy, but the wind blows it in, towards the right. So it's gonna blow phi big W onto phi small w. So we know it. This is true. Okay, it's approximate. Okay, it's actually approximate. Okay, so we already dealt with these two terms. Now we deal with this term. And this one is familiar to us, right? So we just use central differencing scheme, which we are very familiar with by now. So let's have a look. Yeah, let's have a look anyway. So we want to find this guy, d phi dx at e, right? So let's take a look. D phi dx evaluated at e. So first, we stand at e, and then the formula is, if we want to find a derivative, we do this. So immediate right minus immediate left divided by the segment. Okay, so the immediate right is phi e, the immediate left is phi p, and the whole segment is delta x long, right? Delta x. So let's do this. Phi e minus phi p divided by delta x. And we also have to do d phi dx evaluated at the west. D phi dx evaluated at west is, so same thing. We stand at the west, immediate right minus immediate left divided by the segment. Okay, so immediate right minus immediate left, phi p minus phi w divided by the segment, which is delta x. Yeah. Okay, so now we can substitute these values into here. Okay, and also we can substitute this into here, this into here. Okay, so now I'm gonna replace phi e with phi p because we use that by the upwind differencing scheme. And then I'm gonna replace phi small w with phi big W, also because of the upwind differencing scheme. And then this, I'm gonna replace it with the central differencing scheme. So E minus P, and then P minus W. Yeah. So let me check my solution. Make sure I'm on the right track. Okay, all looks good. So let's go ahead and simplify this problem. Yeah. So I'm gonna put it in the standard form that they put, which is like on the one hand side it's just constants, and then on the other side we have W phi P. Sorry, phi W phi P phi E. Okay, so let's go ahead and do that. Uh, oh wait, I forgot this gamma term. Yeah, I forgot this gamma. Sorry, forgot this gamma. Yeah, like that. Okay. Let's factorize out this delta x from both sides. So this side I'm just gonna copy down, and I'm gonna factorize out delta x, and then I'm gonna simplify the numerator. So -1 minus 1 is -2. Then negative times negative is positive. Okay, and then I'm gonna expand these terms. Okay, and now I'm gonna group the terms together. So I'm gonna bring everything to this side and group the like terms together. Okay, so group the like terms together. So this side, when everything's moved across, everything in this side becomes 0 on the left hand side. Now let's start with the W terms. So we have phi W here and another W here. So you see, this negative will become positive. So positive rho U, and then this plus gamma over delta X. Then we factorize out the phi W. Next, we have the phi P terms. So where is the phi P terms? This is the phi P term. This is the phi P term. So you move this to this side. So positive rho U becomes negative rho U. Plus. negative rho u. Then we have negative 2 gamma over x. Then you factorize out phi p. And lastly, we have phi e. Yeah. So the only phi e term is this. So just put it at the back. Yeah. So now you go back to the question and you substitute all the values, right? They already give you rho, u, gamma, and you can find delta x. Yeah. So you substitute all these values in and you should be able to get, so sub values. Okay. Remember it's from the question and you should be able to get this. Yeah. And this is for points 2, 3, and 4, right? So actually, it's not just this. It's actually, you have to sub in phi 2, 3, and 4 in. So for example, for point 2, this would be what? 0.6. So this will be 1. This will be 2. This will be 3. Yeah. And you would do the same thing for points 3 and point 4, right? So this one will become phi, this will be 0.6, then this is phi 2, 3, and 4. And lastly, it'll be the same thing, but now it's 3, 4. Yeah. Okay. So yeah, the equations for points 2, 3, and 4. Now we have to go to the boundaries, the external nodes. So for the external nodes, let's have a look. So I'm going to draw the diagram in the template. So at point 1, we have this. So this is the left-hand side, the NA. This is point 1, point 2, and this is the template. So this is point P. This is east, small west, and we do not have big west in this case, right? Because it's the boundary. So what we will do is we shall reuse equation star. Okay, refer back up to find what's equation star, but I'm just gonna copy it down here. So equation star is just this. Okay, let's have a look. So again, we need to do our approximations. So we don't know what's this and what's this. Okay, so we have to use the upwind differencing scheme. Why up? Sorry, I keep saying differencing. It's just upwind scheme. Okay, it's just upwind scheme. It's not differencing scheme. Just upwind scheme. So these are from the convection terms, right? That's why we will use upwind scheme. They're from the convection terms, so we will use upwind scheme. So let's have a look. What is phi e? So remember we had the fluid velocity flowing this way. So that means phi p will be pushed onto phi e. So we know by the upwind scheme. So let me write down. By upwind, phi e will be approximately equal to phi p. Then let's have a look at phi w. Okay, so have a look. Phi w, there's nothing to the right of phi w, right? There's nothing here. There's nothing here. So we cannot use upwind scheme. Instead, what we use is, we will just use the boundary condition. Because this is at the boundary, right? Remember, this is the boundary node. Okay, this is a boundary. Because it's at the very end of this domain. So let's have a look what the boundary condition did they give to us. Okay, so the boundary condition that they give to us is here. This is actually phi w. Okay, at x equals 0, we have phi w, and phi w is given to be 1. Okay, so we know, uh, so let me just write this down. So by boundary condition, we know that phi w is equals to 1. Okay, yeah, let's check. Yeah, phi a is equal to 1. So let's just call this phi a, which is equal to 1. Okay, so we already deal with the convection terms. Now let's deal with the conduction term. Yeah, the conduction term or the diffusion term. This is also the same thing. So let's have a look. So we want d phi dx at E, right? D phi dx at E. Yeah, we want this. So what is this? So d phi dx at E is equal to, so again, we stand at E. So we stand at E. So to find derivatives in CFD, we take immediate right minus immediate left divided by the segment. So immediate right, which is phi E, and then immediate left, which is phi P, divided by the length of the segment, which is delta X. Same thing, we want this, but now at the west. So again, we will stand at west. Okay, so remember, normally to find derivatives, we want to take immediate right minus immediate left, but in this case, we do not have the immediate left. Yeah, we don't have the immediate left. So instead of using left, we're gonna have to use the point itself. Okay, we have to use the point itself. So we take immediate right. So let me start. Immediate right minus the point itself divided by the length of this segment, which is delta x over 2. Immediate right minus the point itself, which is this, divided by this. Then to simplify it, we can take times 2 times 2. Okay, so that will give us, okay, I'm just going to write it down straight away here. Straight away. So here, I'm going to sub in the values, right? So rho E, I replace it with the upwind scheme, which states that it'll be equal to phi P. Then the boundary condition says that phi small w is equal to phi A. Yeah, right here. And then this will be phi, up here. I'm going to take this. So phi E minus phi P. Phi E minus phi P divided by the segment. Then this, okay. So I'm going to straight away expand this. So 2 times this, 2 times this. So 2 phi P, 2 phi P minus 2 phi W divided by the denominator. So 2 and 2 can cancel. So it just leave me with delta X. Yeah, and then remember what I said? Remember what I said? What is this phi small w? Phi small w is given by the boundary condition. So we can straight away sub this with phi A. Yeah, so substitute that with phi A. So let's keep this to the side. And then we're gonna factorize out the denominator. So factorize this. And then let's simplify the numerator. So in the numerator, what do we have? We have, so minus 1 minus 2 is actually minus 3. And then negative times negative is just positive. Okay, now we expand this side. I'm actually sick if you couldn't tell. Yeah, I got a fever like 2 days ago and still recovering, but yeah, trying to get this video out actually because I'm bored. Okay, so this. Okay, so now let's just collect all the terms together. So on this side, I'm gonna put phi p. So where's the phi p terms? Phi p, phi p. So first we have rho u, and then this plus 3 gamma, sorry, negative 3 gamma, I'm going to bring it to this side, it become plus 3 gamma over delta x, then factorize out phi p. Then on the right, sorry, not to the right yet. Then now I'm going to bring the phi e terms. So where are the phi e terms? We have this. That's it, right? Yeah, that's it. So that will become negative phi, sorry, negative gamma, like that. Then now on this side, I'm going to put all the phi a terms. So here's a phi a term. Negative rho u becomes positive rho u. Then you have this, so plus 2 gamma delta x, and then factorize out the phi a. Okay, so now you substitute all the values, right? Because they give you rho, u, gamma, and you can find delta x. Yeah, so sub in all these values, and don't forget that phi a according to the boundary condition is equal to 1. Okay, so substitute that in, and you should get this. So sub in values, you should get 1.6 phi p minus 0.5 phi e to 1.1. And then you can further simplify this problem. Okay, so who is phi p? See, at p we have 1, and who is phi e? At e we have 2. So phi e is 1, and sorry, phi p is 1, phi e is 2. So let's go ahead. Phi p is 1, and phi e is 2. None. This is correct. Okay, and now let's go to the other end. So we have node 5. So let's draw out the line and its template. So first the line. So this is the NB. This is 5. This is 4. Okay. And then the template, we have this is point P. This is the west. This is small west. And this is small east. We do not have small east in this case. So again, we have to reuse the differential equation. So reuse equation star. We have okay, so let's have a look. We have to do our approximation now. So again, we don't know phi E, we don't know phi W. So let's use the upwind differencing scheme because they are from the convection term. Yeah. So convection term, we need to know the fluid velocity going right side. So who is phi E? Yeah. So phi E will be, the value of phi E will be from phi P. Okay. So the wind will blow phi P onto phi E. Yeah, the wind will blow phi E onto phi P onto phi E. Okay, so that means we know by upwind, the upwind scheme, phi E will be equal to phi P. And then who is phi W? Phi W, the value of phi W will be from here. The wind is gonna push it all the way to here. So uh yeah, another one is phi small w will be equal to phi big W. Yeah. Okay, so we have our convection terms dealt with. So this is dealt with, this is dealt with. Hold on. Okay, now we have to do d phi dx at E. Okay. So we're already familiar with this by now. To find d phi dx at E, you stand at E, then use immediate right minus immediate left divided by the segment. But in this case, we do not have immediate right, right? So instead of using immediate right, we have to use the point itself. We have to use the point itself. So the point itself minus immediate left divided by the segment, which is delta x over 2. Okay, the point itself minus the immediate left divided by this. Okay, so you can simplify this. You can multiply the top and bottom by 2. So this 2 can cancel, and then you expand the top, you should get 2 phi e minus 2 phi p. Yeah, okay. And now we also want this, but evaluated at west. So at west, you take immediate right. So phi p minus the immediate left. So phi big W divided by the length of the segment. Oh, this is delta x. Okay, now you substitute this into the conduction term. Yeah, you substitute it into here. Okay, so let's go ahead and do our approximations. So, phi e, I'm going to replace it with our upwind scheme. So this, phi small w, again, the upwind scheme. Then, the conduction terms, I'll replace it with, yeah, with what we got just now. Okay, so take a look. Actually, we know everything but phi e, right? But so what is phi e? So phi e, let's go back up to our diagram. So because phi e is the boundary, right? So that means phi e is equal to phi b. And phi b, they already given us in the question. So let's take a look at the boundary conditions. Is this. So this is phi b. So it's 0. Okay, so phi b is equal to 0. So by the boundary condition, phi e, so this is the boundary condition, is equal to phi b, which is equal to 0. Okay. So let's just go ahead and do as usual. So factorize out delta x from the bottom. And then, okay, because this is 0, because we know phi e is 0, I'm just going to make it vanish already. This can go away from 0. So what we're left is, in the rest of the numerator, we have, okay, minus 2, minus 1 is minus 3. And then minus times minus is plus. Okay, we expand this to each term. And now we collect all the terms together. So I'm going to put W terms together first. So we have W here and W here. So this becomes positive gamma. And then you factorize out phi W. Then we have the phi P terms. So phi P term, the first phi P term is here. So rho U. Then the next one is this. So negative 3 gamma becomes positive 3 gamma. Okay, so now we have all these values, correct? So we can substitute all the values, so sub values, and you will achieve this equation. Yeah. And then for this problem, phi p is 5, remember? From the diagram. And then phi w is 4. Yes. Okay, so that's it. We succeeded. We have 5 equations and 5 unknowns. So therefore we are able to solve the values of phi 1 to phi 5. Okay, so we know phi 1, phi 2, phi 3, all the way up to phi 5. Yeah, it's solvable. Okay, so we don't need to solve it, but we know it's solvable. Okay, so now I remember at the start of the video, I said I want to do some additional discussions on the upwind scheme. So remember, let's go back to the top. So let's take a recap. What is the upwind scheme? The upwind scheme is an approximation. So we now know that this approximation, uh, okay, is due to the wind. The wind blowing the next phi value onto the neighboring phi value. Okay, it's an approximation to help us get a stable solution for convection problems. So yeah, if there's no convection term, then this scheme can't even exist. It can't even be used to begin with. Okay, so let's talk about the stable solution. Okay, let's call it. So in this problem, we have phi blowing to the right. Correct. So what happens if we have phi blowing to the left? It's a possibility, right? The fluid can always flow towards the left side, right? Depending on how we want to make it flow. So let's have a look. So okay, so usually, right, we don't know what's phi e, and we don't know what's phi small w. Okay, so if instead the wind, the fluid velocity is flowing in this direction, okay, so I think you can guess by the fart analogy. Now it will be this phi big E being blown onto, is being pushed onto uh phi small e. Okay, so phi small e will be equal to phi big E. Okay, and then how do I get phi w? The wind will blow phi p onto phi small w. So phi small w will be approximated as phi p. Okay, so this will be the upwind scheme if the wind is blowing in the opposite direction. Okay, so upwind. It's also upwind scheme. But now u is flowing to the right, which is opposite to what we discussed in this problem. Okay? Now let's talk about the stability. So it's actually possible to avoid using the upwind scheme in convection problems. We can use the central differencing scheme in convection problems, but we need to satisfy certain criteria. Okay? So let's have a look. So I'm gonna draw the template again. This is P E W small w voice. Okay, so again, we always don't know what phi e and phi w is. So if we want to use the central differencing scheme for this, so if we use central differencing scheme instead of upwind scheme. So if we want to use the central differencing scheme instead of the upwind scheme, what would that look like? So this will look like this. So let me show you what the answer is first, and then I'll explain. So phi e will be approximated as phi e plus phi p divided by w. Then phi small w will be phi p plus phi big W divided by 2. So let's have a look. So we don't know what phi e is. So what we do is we take the we don't know what phi e is. So what we do is we take the average of its surrounding neighbors, right? We take the average of its surrounding neighbors. So phi e will be equal to phi big E plus phi p divided by 2. Then we also don't know what phi w is, so we will take the average of its neighbors. So phi p plus phi w, then divided by 2. Phi w is equal to phi p plus phi big W. Whoops, my apologies. Divided by 2. Yeah, if we use central differencing scheme instead of the upwind scheme, so we don't think about the concentrations being pushed onto the neighboring values. What we would do is we treat phi e and phi w as a central value, and after that, to approximate phi e and phi w, we take the average of its neighbors, right? See, we're just taking We just sum up the neighbors and then divide it by 2. That's the average of the two neighboring values. Okay? So what you can think of, so let's go back to the fart analogy, but now we don't think about the upwind scheme, we think about the central differencing scheme. So it's a central differencing scheme, but with a fart analogy. So let's take this person. So this is person A, person B, and this is you. So this person, he takes a fart, and then this person, he takes a fart. Okay? So now, in central differencing scheme, what we do is to approximate the fart at your position. So what we do is we imagine that half the fart comes from A and another half of the fart comes from B. In other words, if you just simplify this value, if you simplify this expression, it would just be phi A plus phi B divided by 2. That's why we just take the average of its neighbors. But when is this accurate? Think about it. Just now in the upwind scheme, right? We think about a wind blowing over, okay? Earlier in the upwind scheme, we think about the wind blowing fart A onto us. So we smell fart A more than we smell fart B, right? But when is this applicable? When is it that I will smell half of the fart concentration coming from A and half of the fart concentration coming from B? This happens when the wind speed is low. When the wind speed is low. Okay, let me put that down. When wind speed. Okay, let me put it. So let me put down the question. When is this accurate? And the answer is when wind speed is low. Okay, and there's low wind speed. Okay, let's think about it. The extreme case of low wind speed, right, is when the wind speed is 0. So that means there's no wind at all. Okay, let's think about a case where there's no wind. Okay, when there's no wind, right, the only way for the farts to reach us is by diffusion. Diffusion. So I think most of you know what diffusion, right? Diffusion is. Diffusion is the spreading of a substance from high concentration to low concentration. So let's think of a simple example of diffusion. Let's say, for example, I have a beaker, right? And then I have clear water. Okay, this is water. Then here I have a dropper. Let me draw a dropper for you. So in this dropper, I have some ink, right? So if I drop ink onto the water, okay, I drop ink. Okay, so for the first few minutes of this, of after I drop the ink into the water, you'll just see a blob of ink over there. Okay, you'll just see a blob of ink over there. But then after a few hours, right, you give it some time. After a few hours, the ink will spread, right? The ink will spread. Okay, then maybe a few days later, the ink. Okay, a few more hours later, the ink will spread again, right? The ink will spread again. Then a few more days, then it'll spread entirely. Okay, so you see, diffusion is the process of a substance spreading from a high concentration, at first it was high concentration, to regions of low concentration. Okay, so in the case of no wind, the only way for the fart to reach you is through diffusion. So what the fart will do is it will slowly spread outwards. Okay? The fart from A and the fart from B will slowly move outwards. And when there's low wind, or when there's no wind at all, it's likely that the fart that reaches you will be in equal proportion. Okay, will be equal proportion from A and from B. See, since it's in equal proportion from A and from B, that means we just say that, okay, since it's in equal proportions, so we just say, okay, the fart that you smell would be half of it coming from A. I'm sorry, something lagging with my computer. Okay, yeah. Half of it coming from A and half of it coming from B. But this is only when the wind speed is very low or when there's no wind speed at all. Okay, so that's how we approximate using the central differencing scheme. Okay, but to be accurate, it's not just low wind speed. What we should satisfy is the PECLET number criterion, the PECLET number. So, if the PECLET number is less than 2, then central differencing scheme in convection problems is applicable. I'll talk about what the PECLET number is. Okay. So, when the PECLET number is less than 2, then central differencing scheme in convection problems is applicable. Okay. So let me show you. This guy, I think he's a mathematician or whatever. He's a scientist. His name is PECLET. I can't remember if it's PECLET like this or PECLET like this. Anyways, the PECLET number should be less than 2 for central differencing scheme to be applicable in convection problems. Okay, so let me have a look at my notes. So the PECLET number, the formula for the PECLET number is given by delta x, so the segment size times rho, which is density. So rho times u, which is a velocity, divided by mu, which is a dynamic viscosity. Okay. So the PECLET number is given by delta x rho u over mu. Okay. So if you want to use central differencing scheme, then the PECLET number should be less than 2. Then it works. So let's have a investigation of the PECLET number. How do I make this quantity less than 2? How do I make this quantity less than 2? Well, the two obvious way is, number one, reducing the wind speed, reducing this, which we already talked about, right? If your wind speed is low, then the likely way of the most likely way of how phi will, okay, which is the fart concentration, how phi will diffuse, right? How phi will reach you is by diffusion. Okay, so low wind speed, then you're most likely to use diffusion to move the property phi. So that means, yeah, central differencing scheme will work. So an equal proportion of phi from the left and the right. Okay, from the left, from the right, equal portion will be coming to you. So that means central differencing scheme can work. Okay. Then another obvious way is to reduce delta x, which is actually, if you reduce delta x, right? You reduce delta x, what you're doing is mesh refinement. Mesh refinement. That's why mesh refinement is important. Okay. So if delta x is smaller and smaller, so you reduce this size. Okay, so let me explain physically what reducing delta x does. Okay, so let me just draw this out. Okay, so actually this is delta x, right? This size here is delta x. Hold on. Yeah, and also this size here is delta x. Okay, so as delta x reduces, so let me use a fart analogy again. And let me see if I can copy the diagram from. Yeah, let's just use this diagram. So as delta x is smaller and smaller, right? So that means A will be closer to B. As delta x is smaller and smaller, it's very likely that the concentrations of phi, the two concentrations of phi, will diffuse in equal proportion. Okay? Because if it's far apart, right? If it's far apart, if it's extremely far apart, this is U, this is A, this is B. If it's far apart, then there's gonna be in sufficient time. There's sufficient distance and time for the wind to blow phi A towards U. Yeah. There can be sufficient time for phi A to blow towards you. So that's why decreasing the distance will will increase the likelihood that phi A and phi B will reach the center point in equal proportion. Okay, decreasing delta x will increase the likelihood that phi A and phi B will diffuse towards the center in equal proportion. See, in equal proportion means central differencing scheme. Okay, yeah. So the moral of the story is, if you want to make your PECLET number small so that you can use the central differencing scheme, there are two obvious ways, which is when delta x is sufficiently low, or the wind speed u. Yeah, the wind speed is sufficiently low. Yeah. So these are the two ways in which central differencing scheme can be used in convection problems. Yeah. But for the most part, we're gonna be using upwind scheme. Yeah. So upwind scheme is better suited when the wind speed is really strong. Yeah. Because when the wind speed, you think about it physically, when the wind speed is strong, then if you're at phi e, right, then it's likely that the neighboring value's concentration will be blown towards you. Yeah. You can think about it that way. If you found this to be a helpful guide into understanding the upwind scheme, please remember to support me on PayPal or Coffee to help the channel grow. Thank you.